Have you ever, like, tried to make a computer program go faster by just throwing 8 times the resources at it?
Oh, yeah. I mean, that's the standard developer instinct, right? Just throw more hardware at it.
Exactly. But then you sit back and watch it inexplicably slow down to an absolute crawl.
Hmm.
It is so frustrating.
It really is. It defies all common sense.
Right. And that is exactly the frustrating, invisible reality of one of the most notorious roadblocks in the entire world of programming. So our mission today is demystifying that roadblock. We're diving deep into a really fascinating narrative-driven blog post by Aaron Rose. It's called The Secret Life of Python Understanding the GIL.
It's a great piece.
It really is. And this deep dive is for you, whether you're, a seasoned software developer writing huge enterprise applications or a data scientist crunching massive data sets, or, well, honestly, even if you are just insanely curious about the hidden mechanics of how computers actually think.
Yeah, because it touches on such a fundamental flaw in how we assume computers work.
Exactly. And to unpack this mystery, Aaron Rose drops us into this brilliant framing device. He actually places us inside this grand atmospheric Victorian library in London.
I love that setting. It's so unexpected for a coding tutorial.
Right. Like we are talking dark wood paneling, towering bookshelves, those rolling ladders. And in this library, code quality isn't just some metric to hit for a quarterly review. It is an unspoken absolute objective. Craftsmanship is paramount.
It sets the stakes perfectly.
It does. And it is here that we meet our two main characters. We have Margaret, who is this brilliant senior software engineer, and Timothy, her really highly capable junior colleague.
And what's fascinating here is how the author uses this incredibly vivid, almost cinematic library setting to ground a highly technical problem. It's a problem that almost every single Python developer eventually hits. We are looking at the illusion of multi-threading speed.
The illusion of it.
Yeah.
Because it's not real.
Right. It's a concept that seems flawlessly logical on the surface, but underneath, the architecture behaves in a way that, well, it completely defies our basic intuition about how work gets distributed.
Yeah, you just assume more workers equals faster work.
Exactly. And by anchoring this in a story between a mentor and a mentee, the source text takes this structural bottleneck, which usually just lives in dry, boring, technical documentation, and turns it into a genuine mystery. We actually get to solve it right alongside Timothy.
So Timothy is actually feeling pretty confident as our story begins. He has just mastered some advanced concepts in his training, specifically things like threads, locks, and queues.
Which are not easy concepts to grasp, to be fair.
No, not at all. And his current project is this chess club application, and it's been running flawlessly. But, he wants to push the boundaries of what this app can do, so he decides to add a brand new feature called Grandmaster Analysis.
Ooh, that sounds intense.
It is. This isn't just some basic function to move pieces around a digital board. This is a heavy, intensive math engine. It needs to calculate, like, millions of possible chess positions to find the absolute mathematically optimal move.
Right, which represents a classic example of a CPU-bound task.
A CPU-bound task, meaning the processor's doing all the heavy lifting.
Exactly. It requires raw, sustained computational power. The processor has to just sit there and physically churn through millions of sequential mathematical operations. It can't take a break. It's just math, math, math.
So Timothy looks at his workstation, right? And he sees he has an 8-core processor.
Yeah.
He has this massive amount of hardware horsepower sitting right in front of him.
Beast of a machine.
Yeah. So he goes to Margaret, and he tells her his plan. He assumes that because he has an 8-core processor, he can just initiate 8 threads, 1 thread for each core.
Makes perfect sense, logically.
I mean, the logic seems bulletproof. If you have 8 workers, and you give them all an equal piece of the job should get done in an eighth of the time. So he writes the code, he initiates the 8 threads, and he pulls up his CPU monitor to watch this Grandmaster Analysis just fly.
And then the reality of the underlying architecture kicks in. And it is a horrifying realization for him.
Total disaster.
Oh, absolute disaster. He runs the program, and not only does the analysis fail to go 8 times faster, it actually takes significantly longer than it did when he was only running a single thread.
Wait, longer?
Longer. And when he looks at his CPU monitor, the dashboard showing what the computer's brain is actually doing, he sees that only one of his 8 CPU cores is doing any real work. The other 7 cores are practically idle.
Okay, let's unpack this. Because I read that and immediately thought Timothy had just encountered a hardware bug. Like his computer was broken.
Oh, I'm sure he thought the same thing.
Right. But he verified that his threads are all healthy and his code was totally correct. Yet, he hit this invisible glass ceiling. He gave Python 8 hands to work with, but Python stubbornly kept 7 of them tied behind its back.
That's a great way to put it.
If I try to visualize this symptom here, imagine Timothy is managing a high-end restaurant kitchen.
Okay, I like where this is going.
He has a massive dinner rush coming in, so he hires 8 master chefs. He has 8 stoves. He expects the dinner service to be incredibly efficient. But instead of cooking, these 8 master chefs all crowd around one single cutting board.
Oh, no.
Yeah, they're bumping elbows, knocking over ingredients, and they slow the entire dinner service down to a crawl. The extra help actively made the kitchen less efficient. Why'd the extra help make things worse?
Well, in the library, Margaret doesn't just hand Timothy a technical manual to explain this phenomenon. That's not her style. She walks right over to a whiteboard and draws a picture. She draws the Python logo, and right around it, she draws a giant, heavy padlock.
The padlock?
Yes. She tells Timothy, you've met the GIL, the Global Interpreter Lock. That lock is the exact reason your chefs are bumping elbows.
Margaret offers this fascinating analogy in the text to conceptualize this lock.
Uh,
She tells Timothy to think of Python like a very sophisticated, high-end talk show.
right. The talk show stage.
Yeah. You can have as many guests on the stage as you want. Those guests represent your threads. You can have your 8 master chefs sitting right there on the stage. And while they're sitting there, they can all think, they can look at their notes, they can prep, and they can wait for their turn.
But Margaret draws a single microphone in the center of that stage. There is only one microphone.
Just one.
Just one. In the standard version of Python, which is called CPython, only one thread is allowed to speak at a time. And in computer terms, speaking means executing a line of bytecode. Only one thread can execute bytecode at any given millisecond.
Wait, bytecode, let's clarify that. That's the intermediate machine-level translation of the code the developer actually typed, right?
Yeah.
The actual instructions the computer's reading step by step.
Correct. When you write Python code, the system translates it into bytecode, which the Python interpreter then actually executes. The GIL, that Global Interpreter Lock, is essentially the stage manager standing off in the wings, holding that one single microphone. And they are forcing everyone on stage to share it.
So it doesn't matter how big the stage is.
Not at all. It doesn't matter if your machine has 8 cores or 80 cores. The stage manager only has one mic. When Timothy spun up his 8 threads for the Grandmaster analysis, he put 8 people on the stage to do intense, continuous math out loud. But they all had to fight over that single microphone.
Wow. If you've ever felt overwhelmed trying to multitask and wished you could just clone yourself to get more done, you will completely understand Timothy's frustration here. I mean, he cloned his workers, but Python only gave them one mouth to speak with.
Exactly. And because of that, they spent more time fighting for the mic, passing it back and forth, than they did actually doing the calculations.
So that's where the slowdown comes from.
Yes, that overhead, the constant switching of context, the passing of the mic, that explains why the process actually took longer than if he had just let one person hold the mic the entire time. It's a bottleneck by design.
Okay, here's where it gets really interesting. Because if I'm Timothy, my immediate reaction is just, why? If I have 8 processor cores, why can't I just have 8 microphones? Why did the creators of Python put a padlock on their own language?
It is an intentional bottleneck, and the motive behind it is arguably the most crucial concept for any Python developer to grasp. It all comes down to memory safety and a very specific mechanism called reference counting.
Reference counting, okay.
So behind the scenes, Python is constantly managing memory for you. Every time you create a variable or list or any piece of data, Python creates an object in your computer's memory. But to know when it can safely delete that object to free up space, Python keeps a running tally. It tracks how many times that specific object is being referenced or used anywhere in your code. This tally is the reference count.
Right. So if 3 different parts of my chess code are looking at a specific list of chess moves, the tally for that list is 3.
Yes, exactly 3. And when that tally hits 0, Python's garbage collector just sweeps in and deletes the object to keep your computer's memory clean and efficient.
Makes sense.
Now, imagine a scenario where you have multiple threads, multiple microphones, all running simultaneously without any kind of lock. Thread A and thread B both finish using that list of chess moves at the exact same millisecond. They both try to update the reference count tally at the exact same time.
Oh, I see. A race condition.
A catastrophic race condition, the tally gets corrupted.
Because they are talking over each other.
Exactly. It might drop to 0 prematurely, causing Python to delete data that another thread was actually still relying on, which, by the way, immediately crashes your entire program.
Not ideal.
No. Or, alternatively, the tally might miss a decrement entirely and never hit 0. That causes a memory leak that slowly consumes your computer's entire RAM until it freezes.
Man, that reframes my kitchen analogy completely.
Yeah.
The chefs aren't just crowding around a cutting board. It's more like they all have their own stoves, but there's only one single refrigerator in the kitchen holding all the ingredients.
Yes.
The GIL is basically the bouncer standing at the fridge door. He is there to ensure that two chefs don't reach in and grab the exact same egg at the exact same millisecond and smash it, right? Ruining the ingredients for everyone. The bouncer enforces order to prevent data corruption.
That is the exact underlying mechanism. Margaret explains to Timothy that the GIL prevents threads from accidentally corrupting Python's internal memory structures. Back in the early days of Python's development, the creators needed a way to keep this internal reference counting simple and thread-safe.
So they just locked the whole thing down.
Yep. The most reliable way to do that was to lock the entire interpreter. You lock the room, you hand out one microphone, and you guarantee that no two threads can ever mutate the internal memory at the same time.
So if we connect this to the bigger picture, the creators made a profound, deliberate trade-off here. They looked at the landscape of programming, and they chose to sacrifice true parallel processing, the ability to run raw computations simultaneously on multiple cores in exchange for incredible internal stability.
They did. They wanted a language that was safe, reliable, and easy to manage under the hood, even if it meant putting a speed limit on heavy math. And honestly, that trade-off is a major reason why Python became one of the most popular and versatile programming languages in the world. It is so accessible because it handles all of that terrifying memory management safely behind the scenes.
Now, the source text does mention a fascinating detail in this cheat sheet that Margaret gives Timothy. This lock, this bouncer, is specific to CPython, which is the standard default version of Python that most people use.
Right.
But alternative versions do exist. She mentions things like Jython and IronPythons, which are built differently and actually don't have a GIL at all, so the ceiling doesn't exist everywhere.
True, but she notes those are much less common in a specialist's daily toolkit. For the vast majority of developers out there, CPython is Python, which means the GIL is the reality you operate within.
Which brings us right back to Timothy's dilemma. I mean, he understands the memory safety aspect now. He respects the bouncer at the refrigerator, but he still has a grandmaster analysis engine that needs to run. And he still has an 8-core processor sitting there completely idle. So is Timothy just stuck? Can he ever use his whole 8-core processor for this?
He can, but not with threads.
Right, because if threading is the wrong tool, because the single microphone, and the bouncer is never going to let them access the fridge simultaneously, threading seems totally obsolete now.
Yeah.
If I'm Timothy, I'd just use multiprocessing for everything, give everyone their own stage, and be done with it.
Well, not so fast. Margaret does introduce multiprocessing as the solution for his chess engine, absolutely, but she makes it very, very clear that it is not a silver bullet for everything. Because with multiprocessing, you are creating entirely new independent processes. Every single worker gets their own stage, their own microphone, their own completely separate memory space, and their own totally independent copy of the Python interpreter.
Oh, wow. That is a massive paradigm shift. Instead of sharing one kitchen, you're building 8 completely separate restaurants.
Exactly. And because they are separate restaurants, they each have their own refrigerator and their own bouncer. They don't have to share the GIL at all. Timothy can finally use all 8 CPU cores to run his grandmaster analysis simultaneously.
That's great.
It is, however, building 8 separate restaurants comes with a massive cost. Memory overhead.
Ah, I see.
Booting up an entirely new stage means loading another full copy of Python into memory. If your base application requires, say, 500 megabytes of RAM to run, multiprocessing just turned that into 4 gigabytes. If you try to use multiprocessing for every minor task, your system will literally run out of memory and grind to a halt.
Oh, so you can't just spam it everywhere. That makes Margaret's decision guide incredibly valuable then. It isn't just about how to go faster. It's a structural rulebook for resource management.
Exactly.
Let's break down her cheat sheet because it maps out exactly when you should use which tool. So the first rule covers the heavy math and number crunching.
Right, the CPU-bound tasks. This is your grandmaster analysis. For these tasks, you must absorb the memory cost and use multiprocessing. You need separate stages so the CPU cores can calculate simultaneously without fighting over a single microphone.
Makes total sense. But the second rule in her guide dictates when you should absolutely still use threading, and it covers I/O-bound tasks. I/O standing for input-output.
Yes. An I/O-bound task is a situation where your program is interacting with something outside of its own brain. It might be waiting for a file to save to a physical hard drive, or querying a database, or waiting for a server across the country to send back a web page.
So the computer's processor isn't actually doing any math during that time. It is just sitting there waiting for data to travel across a wire.
Exactly. And in the world of computing, waiting for a network response takes milliseconds, which is an absolute eternity for a CPU that operates in nanoseconds.
An eternity.
Yes. So during that eternity, the thread is not executing bytecode, it's just waiting. So what does it do? It voluntarily drops the microphone, it hands it back to the stage manager, and basically says, hey, I'm just waiting on file here, someone else can talk for a bit.
Oh. That completely justifies why threading is still so vital. If you have one thread requesting an image from a server, while it waits for the image to arrive, it hands the mic to another thread, that is, say, writing a log file. And then that thread hands the mic to a thread updating the user interface.
Exactly. They pass it around.
Because they are voluntarily sharing the mic whenever they pause to wait, a single stage works perfectly. You don't need to build 8 separate restaurants if your chefs spend most of their time just standing around waiting for delivery trucks to arrive.
It's a highly efficient use of resources.
Yeah.
And the source text points out that the cues, the tools Timothy learned about in a previous fictional episode, they are still highly useful here. The GIL doesn't render cues unsafe at all. It just limits how much bytecode can be executed simultaneously. For organizing tasks that are largely waiting in line, threading combined with cues is very often the optimal architecture.
So cool. But Margaret's guide includes one final scenario, pushing the boundaries of the single stage even further. What if you aren't just waiting for one file or one image? What if you were building a massive chat server and you need to handle like 10,000 simultaneous network connections?
For that massive scale of I/O operations, her cheat sheet recommends a completely different tool called Asensio.
Asensio, going back to our talk show analogy, Asensio is described as efficient juggling on a single stage. It's like having one incredibly fast, hyper-aware host who can talk to 10,000 guests. The host doesn't wait for a guest to finish a long, rambling sentence. The very millisecond a guest pauses to take a breath, the host pivots and addresses the next guest. It is highly orchestrated, single-stage concurrency based on an event loop.
It's brilliant. It requires a completely different style of writing code, but it is deeply, deeply powerful. Ultimately, Aaron Rose's narrative is teaching us about the architecture of bottlenecks. If you understand the mechanics of the GIL and you understand reference counting, you know exactly why the bottleneck is happening in the first place.
Yeah.
And once you know why it's happening, you look at Margaret's cheat sheet and you know exactly which tool to reach for.
So what does this all mean? It fundamentally changes how you approach problem solving in this language. To go faster with heavy math, you don't try to manage the chaos in the room better. You absorb the memory cost, escape the single stage entirely, and you build more rooms. Timothy looked up at that metaphorical glass ceiling in the library, and he realized the limitation wasn't a bug. It was the foundational physics of the environment he was working in.
I think the defining takeaway here, for anyone listening who writes code or designs systems, is deeply internalizing that difference between an I/O-bound task and a CPU-bound task.
Yeah.
That distinction is the master key to unlocking performance.
It really is.
Once you map the behavior of the global interpreter lock, you will never again throw standard threads at a heavy math problem and sit there wondering why your dashboard shows idle cores while your program moves backward. You see the invisible bouncer at the door clearly, and you know exactly how to architect your way around him.
We know from the text that alternative versions of Python, like Jthon, exist without this lock. And we now deeply understand that the GIL was integrated into standard CPython to protect its internal memory, specifically that reference counting mechanism.
Right.
Yeah.
But, that leaves me with this massive, really provocative question to think about. What if a team of engineers actually figured out a way to safely rip the GIL out of standard CPython tomorrow? Right. If they solved the reference counting race conditions without needing the padlock at all, how much of the world's legacy code that has implicitly relied on the GIL's rhythm and its safety net for decades, how much of it would suddenly break?
A terrifying amount, probably.
Would the resulting speed boost, the ability to finally use all those cores natively on a single stage, actually be worth the sheer chaos of rewriting computing history? It's this wild balance of progress versus stability that the software community wrestles with every single day.
It's a great question to leave on.
Thank you for joining us on this deep dive into the Victorian Library, the talk show stage, and the hidden mechanics of Python. Remember, keep questioning the invisible ceilings in your own work. Sometimes the solution isn't to work harder in the room you are in, it's to build an entirely new stage. Until next time.